Good afternoon, everyone. I hope you had a good weekend and that you all are doing well. The first thing I want to touch upon today is I want to pick up on our simple harmonic motion conversation we had last week. So last week we kind of refreshed our minds on the equations for position, velocity, and acceleration as functions of time for simple harmonic motion. Now, one thing we didn't talk about was how do you find x max, v max, and a max, and we did need to use a max on the homework for last week. So I have a full solution to homework question 2 from last week up on our Blackboard if you haven't seen that yet. So, but I want to focus on what those equations are just so you kind of have those in your brain and where did they come from. So that's going to be our first topic. So recall from last week that the position of a wave is just x of t is equal to a cosine 2 pi times the frequency times the time, where a is our amplitude. Now, if you want to know the maximum value that our displacement can be, then, well, a is a constant, so that's going to stay the same no matter what. So x max, we're going to have a. Now, what is the maximum value that cosine can take on? Well, the maximum value cosine can be is 1. So we're just going to have a times 1, which means that our maximum displacement is going to be our amplitude, which makes sense because definitionally the amplitude is the maximum displacement for simple harmonic motion. So next we'll look at velocity. So velocity is two pi times the frequency times our amplitude. We have a negative sign out front. And then we have times sine of 2 pi times the frequency times the time. So if you want the biggest this can be, we can ignore the negative sign. So we're going to get v max, because sine is going to oscillate between -1 and +1, so if this is -1, the negative sign will go away. 2 pi, f and a, those are all constants, so they're going to stay the same. And then if we have -1 here, -1 here, so that's going to give us a value of +1, and that's going to be the maximum that negative sign can have for value. So our Vmax equation is going to be just 2 pi Fa. So are there any questions so far? Alright, so the last thing is our maximum acceleration, and this was the one that we needed for last week's homework. So our acceleration as a function of time, we found out last week was a of t is equal to, and then we have parenthetically 2 pi times the frequency, that whole quantity squared, times our amplitude. And we're going to have a negative sign out front again, and then this time it's going to be cosine 2 pi frequency times the time. And we're going to use the same reasoning as before, so all this stuff out front is a constant, so a max is equal to this stuff, 2 pi f quantity squared times our amplitude. And then if we lump the negative sign in with cosine, well, the maximum value that negative cosine could be is +1. So this is going to be times 1. So our A max is equal to 2 pi times our frequency squared times our amplitude, and that's the maximum value that can take on. So are there any questions on this? And remember, if you have questions, you can just hop in at any point in time. You can use your mic or you can use the chat. The chat, I think there's a little bit of a delay on my end, or maybe I'm just not looking at the screen enough, so it may be a little slower for me to get to you if you use chat, but it's still a perfectly viable option to ask me questions with. All right. Are there any questions on any of the material that we covered last week? All right, if there are no further questions, what I want to focus on today is the material from sections 15.2 and 15.3. So last week we kind of jumped ahead and went to 15.4. And so this week we're going to hop back and we're going to focus on 15.2 and 15.3 for today primarily. So 15.2 talks about the speed of a wave, how that's related to the material through which it travels. And you're going to need that for the first 3 questions of the homework. And then 15.3 focuses on snapshot graphs and history graphs, and you'll need that for the next 3 questions of homework. So what I hope to do by the end of today, to have for you, is all the material that you need to do the first 6 questions on this homework set. So we're going to start in section 15.2, which is on some of the basic properties of a wave. So let's suppose we have a wave and it is fixed at 2 ends. And we'll talk about fixed ends a little bit more later, but all a fixed end means is it can't move past this point. So you can think of this like maybe we've taped both ends of this string to the wall or something like that. So they both are being held fixed. So the wave can't extend beyond them. So there could be more string past these ends, but this is the region through which the wave can travel. Now it turns out that how fast this wave will travel depends on the material properties of the string. So our string is going to have some mass, and we're just going to use a little m. So little m is the mass of our string. And our string is also going to have some length. Now I got a good question in my last section about how do we measure our length. We're going to measure it between the fixed ends of the string. So even if we have more string that kind of extends beyond here, we're measuring between basically the 2 fixed points on the string. So from here to here, that's going to be our length L. So are there any questions on that so far? All right, so if we know the mass of the string and the length of the string, we can calculate what's called the linear mass density, and we use the Greek letter mu to denote it. So this is just linear mass density, or sometimes mass density. The linear there is because we're treating the string as though it's one-dimensional. And the mass density, it's a lot like a regular density, but instead of having mass over volume, we're going to have mass over length. Where length would be your one-dimensional equivalent of volume. So this m is the mass of our string. And this L is our length. And it turns out that the linear mass density has a big impact on how fast our wave can travel. So if mu is really big, the wave is going to move more slowly. If mu is really small, then our wave is going to move faster through our material. So are there any questions so far? All right, so the other property it turns out that matters a lot for the speed of the wave is the tension in the wave. So if we're holding the two ends of our string fixed, we're going to have some amount of tension in the string. And so it turns out the speed of the wave is related to the linear mass density and the tension through this equation. So we have our speed v is equal to the square root of our tension divided by our linear mass density. So this t here is our old friend tension. Mu again is linear mass density, which I'll just denote as mass density here. And v is our speed. So the first three questions on the homework set this week really just involved using this equation in different ways. So we're going to do an example real quick that will help you get a handle on how to use this equation. But before we get to this example, are there any questions? All right. So for our example, let's suppose that there's a piece of string lying on the floor. And we happen to plop our laptop down on the end of the string. So our laptop is holding one end of the string in place. And let's suppose that we have a textbook on the other end of the string. So our string is being held fixed between these two objects. And Cupcake sees a string lying on the floor, and so naturally she reaches out and tugs on our string. So that's her little paw. And when she tugs on the string, that's going to introduce a wave into the string. So let's suppose that our string weighs 20 grams. So M is 20 grams. Let's also suppose that the length between the book and the computer is half a meter. So this length here is our length L. So going from the end of the book to the end of the beginning of the laptop. And let's suppose that our string here has a tension of 5 newtons. So we want to know what speed will the wave then travel at. To figure this out, we're just going to need to first find our linear mass density, and then we're going to go to our speed equation. So our linear mass density is just mu equals m over L, where our mass, this is in grams, we're going to convert to kilograms, so that's going to be 0.020 kilograms. And we're going to divide that by our length, which is already in meters for us, so 0.5 meters. And we're going to find out that this is equal to 0.040 kilograms per meter. So that's our linear mass density. So to find our speed, all we're going to have to do is plug that and our tension into our equation for the speed of the wave. v is equal to the square root of t over mu, so that's going to be the square root of, we said our tension was 50 newtons, and we're dividing that by 0.040 kilograms per meter, and this works out to be 11.18 meters per second, or that's not 50 newtons, that's 5.0 newtons, or 2 sig figs, 11 meters per second. So are there any questions on this one? All right, so the next topic I want to focus on today are snapshot graphs and history graphs. Now, normally when I'm teaching this, I have like a nice giant whiteboard that I can work with, so I can have multiple graphs up on the screen at once. Unfortunately, with this tiny little whiteboard, there's no way I could have a bunch of different graphs easily accessible at once on a scale where you could view them. So what I've gone ahead and done is I've made a little bit of a slideshow, and I'm going to make this available on our Blackboard. So I'm going to kind of walk you through an introduction to snapshot graphs and history graphs. Feel free to, as we're going along, to ask me any questions and pause me at any point in time if you have any. But I'm going to switch over to my screen view real quick and we'll go through that. What is a snapshot graph? Well, a snapshot graph is basically just, it shows all the points of a wave at a particular instance in time. So you can think of it like taking a picture of a wave. So if you have, a wave on a string and you took a picture of it, you'd be able to see where each individual point's x and y coordinates are. That's basically what a snapshot graph is. So I have here this example where we just have this little wave shape, and I'm going to call this the t equals 0 time. So let's now suppose that our wave is traveling to the right at 1 meters per second. Well, if it has a speed of 1 meters per second, what that means is that all the points on the wave are going to shift over by 1 meter in 1 second. So you can see one end of the wave is starting out at 0 meters, the next one is starting at 4 meters. So after 1 second, the ends are now at 1 meter and at 5 meters. So for snapshot graphs, generally, you have a speed, or I guess a velocity, because we have the direction as well. And then you'll be able to, you have to figure out where does the wave go over time, and you're just shifting it over time. So after 2 seconds, well, one end moves over by 1 meter and the other end moves over by a meter also, and everything in between moves over by 1 meter. So our graph just translated by 1 meter. After 3 seconds, the same thing. After 4 seconds, the same thing. So we're just moving everything over by 1 meter each second. If we had looked at a half second, everything would have shifted over by half a meter. But since we're looking at whole seconds, everything's shifted over by a meter. Now we're going to dabble a little bit in section 16 here, or chapter 16 here, because in 16 it introduces the idea of fixed ends. And I think it's helpful to start talking about them now. I don't think your homework this week deals with fixed ends yet, but it will be on future homework assignments, so I think it's helpful to start seeing them now. So let's suppose that the ends at 0 meters and at 8 meters are fixed ends, meaning they can't move. So maybe our string is clamped between clamps at 0 meters and 8 meters, and so our wave can only travel between those 2 points. Well, what happens to our string here? It turns out when you have a fixed end, the graph reflects, so it basically becomes like a mirror image of itself, but it's mirrored not only over the y-axis, but also over the x. So to figure out what happens mathematically, the way we figured out how to do this is we draw an imaginary wave. There's a mirror image of this that's also flipped over the x-axis. So this is our imaginary wave. And it's going to meet our real wave at the 8 centimeter mark, or 8 meter, sorry, mark. So if we want to figure out what happens for times beyond 4 seconds, what we're going to have to do is shift our real and imaginary waves over. We basically pretend like our string is longer than it really is, so 8 centimeters or 8 meters, sorry, is not the cutoff point anymore. We just shift everything over by 1 meter. So at 5 seconds, we shift this wave over by a meter. We also shift this wave over by a meter, and then we have to add them mathematically. So this is where things get a little bit tricky. And if you have any questions, again, don't hesitate to ask. And also, it's okay if you don't completely digest this right now. Again, we're not going to have homework questions on this probably until next week. But if we want to add these two together, what we do is we think about the slopes of these lines where there's overlap. So from 5 meters to 7 meters, we only have the blue line. So if we were to graph our graph for that part of it, it's going to look just like this right here. But the problem is this region here. So from 7 to 8, we don't care about what happens beyond 8 because that's not real. But what's happening between 7 and 8 meters, we have to add the slopes of our graphs together to figure out. I haven't given you the equations here I used to generate them, but this one has a slope of -0.5, and this one also has a slope of -0.5. So -0.5 and -0.5 would be -1. So we should get a line over here with a slope of -1. So this is what it's going to look like. So instead of having, a shallower slope, we now have a steeper negative slope over here. So are there any questions up to this point? All right, so if we continue along, at 6 seconds, our blue wave moves over by a meter, everything shifts over, and our purple wave also moves over by a meter. And now you can see everything is overlapping, so we no longer have that space where we can just draw it. We have to add everything, and we can ignore what happens after 8 again because there's no actual place for the wave to travel there. So if we're looking at what's happening between 6 and 8 meters, if we look here, going from 6 to 7, we have this blue curve here has a slope of 1 slope of 1, positive 1, yep, and this one has a slope of -0.5. So if we add those together, we're going to have x minus 5x would be 0.5x, so we're going to have a slope of 0.5. And so our line is going to go up to 1/2, and then if we go back over here, so we have here from 7 to 8, this curve is a flat fixed 1. And this one has, again, a slope of -0.5. So it's going to be taking away from that, and what we're going to end up having happen is that our curve is going to go from 0.5 meters all the way down to 0 again at 8. So you're going to get a graph that looks something like this. And my amplitude is wrong on this one. It should be 0.5 meters. So I'll fix that before I send the PDF out to you. But it will look like this. So are there questions to this point? All right, so at 7 seconds, our purple wave and our blue waves move over again. And now you can see that the purple wave is kind of taking over. So we're still going to have a little bit of impact from the blue wave, but from 5 meters to 7 meters, it's all the purple wave. Now, this here is a constant -1. This has a slope of +1. So we're going to be going from, this starts out at 0 and it goes up to 1. So we're going to have 1 at the peak, but then by 8, we're going to be down to 0 again. So our wave is going to look like this. And again, it's a little bit tricky to just see it on the board. It's helpful to draw these things out. So if it's not making complete sense right now, it may help if you try adding these out mathematically on your own. So now, at 8 seconds, this is where the waves completely pass each other. And from here on out, until we hit 0, this wave is going to be the only one that's contributing to our graph. So if you draw this from, we draw this, it's just going to be this wave. So that would be what our graph looks like. And beyond 8 seconds, this one's just going to kind of inch over until it hits 0, and then we're going to have the reflection process again. We could draw an imaginary wave up here off to the side, and they're going to move back and forth in that exact same fashion. So are there any questions about snapshot graphs before we move on to history graphs? Also for this week, the snapshot graphs, again, you're not going to have to worry about the fixed end. I don't think. I looked at the problems and it looks like they're just looking at snapshots in time where you're not worried about what's happening at the end. So, but it is important to understand what happens at the ends because that will come into play later on in the semester. So a history graph just tracks a specific point of the wave through time. And we can pick any point we want. So we're going to pick the point x equals 6 meters, but we could pick 8 meters, we could pick 4, we could pick anywhere in between. So I'm just going to pick 6 meters. And we're going to start at 0 seconds. So this is the snapshot we had at t equals 0 seconds from before. And we can see already that so the wave is moving in this direction, it's moving to the right at 1 meter per second. So for 2 seconds, there's not even going to be anything happening here because it's going to take the wave 2 seconds to reach this point. So if we map out just the first 2 seconds, we're going to have a horizontal line right along our axis. Now, in this case, we're graphing our amplitude versus time. So with our snapshot graph, we have our position in the y direction and our position in the x direction. For a history graph, we're looking at a specific x point in time. So we'll still have our amplitude we're graphing, but now it's time on the x-axis. All right, so let's look ahead to 2 seconds. So we can see 2 seconds is when we finally reach this point. And if you think about what happens as this wave moves forward, well, it's going to start out, this point here is going to be at 0, and then it's going to slowly kind of creep up. If you think about this wave slowly inching over until it reaches this point here. So as our wave travels over, eventually after 2 seconds, this point here is going to be up here. So if we plot what that looks like, we're going to go from, we start out at 0 and we go up to 1. So it looks kind of like the reverse of our wave because this front is what's rising with the point. So that's what it's going to look like. So now if we jump ahead to 4 seconds, this is where our flat stretch is going to reach 6 meters. So it's just going to be flat for that whole second. You know, you can just think this point is what's passing over our wave. So it's just flat. Now, here we have to start thinking about the imaginary wave. And I've picked things this time around so that the imaginary wave isn't going to make a difference here, but there are times when it would. So if we pick 7 meters instead, we would have some interference. But if we think about what's happening with our imaginary wave, it first shows up at 4 seconds. And for 2 seconds, it's not even going to reach our wave. So if we think about what's happening from 4 to 5 seconds and from 5 to 6 seconds, we're still going to be relying only on our blue wave. So we'll look at our graph. It's just going to be, because only this wave is going to be reaching this point, you know, the tail of this curve is going to move here before this one even hits it. We're going to get the rest of our wave. Now what happens after 6 seconds? Well, the blue one's going to move past it. The purple one's going to be moving in this direction. So the purple one's going to be what's raising this point or lowering it. And so for the next 4 seconds, it's going to end up looking like this. So that would be a history graph for our wave. So are there any questions? All right, well, if there are no further questions for now, the plan for Wednesday is, well, we'll first see what material Mr. Judish gives us between now and then. I don't want to end up duplicating the material that he's sharing too much, but our plan is going to be to focus on sections 15.5 and 15.6 if he hasn't already covered those, because that will give us the information we need to solve the last 3 questions on the homework. And then also answer any homework questions you have during that time. And remember, you can always shoot me an email. So if you're working on the homework and there's something that doesn't make sense or you think needs to be clarified, you can send me an email in advance and I'll make sure to have that on the agenda for Wednesday's meeting. Or if you're looking ahead in the textbook and you see something you're not clear on, you can also ask me about that. But if there are no further questions, then have a great day.
Hello, folks.
The camera doesn't like you.
No. Today we're going to learn
Yeah, you're not teaching them, Brian.
about how to draw smiley faces.
But don't draw too much on the whiteboard. It gets really gross very quickly.
Amber doesn't want me to draw smiley faces, so
You can draw a smiley face.
you guys are out of luck. Sorry. No smiley faces for you. All frowny. All frowny faces.
Brian, draw a smiley face, please.
There you guys go. A grade A smiley face. It's not creepy at all.